Good morning, everyone. Today we are looking at Unit 2, Lesson 9, Determining Polynomial Equations from Points. So we're going to start today's note by sketching any quartic function with x-intercepts -3, -1, 1, and 2. So I'm going to sketch that on the first graph here. So just any quartic function that has those zeros. 1, 2, 3. So a 0 at -3, -1, 1, and 2. I'm going to have a quartic function with n behaviors that both point up. And I'm going to have not cross the x-axis so much, but cross a little bit. Okay, so that's one quartic function that might have those x-intercepts. But let's sketch a second quartic function with the same x-intercepts and opposite n behavior this time. So we are pointing up on the first one, so we'll create another one and point down. -3, -1, 1, and 2. So this time I'm going to have n behaviors that point down. And I'm going to make this one a little skinnier of a w. I'm going to make them go up and down past that x-axis a bit more, just to show that a quartic could look very different, even with the same zeros. So in other classes or in other courses in math, you would have noticed that where we could kind of stretch out a function, and there was a variable within the function that caused this stretch or compression, and that was your a variable. Okay, it's usually the leading coefficient on a function. So let's just say your a value. Let's recall. A value represents a vertical stretch, or compression. All right, so when we have an x-intercept that opens up, but it's kind of a wider w, we could then also have a quartic function that has the exact same zeros, but it's a little skinnier and stretched, and there's some a value that's causing that stretch. So let's look at how we can represent this. So how many quartic functions have x-intercepts of -3, -1, and 2? And we can say that there are infinite possibilities. Meaning that if we really wanted to write the general form of this equation, we could write that f of x is equal to, and before we write our zeros, we're going to put in that a value. And we'll write x plus 3, x plus 1, x minus 1, and x minus 2. And we can say that this equation, this represents the general form, or the general equation for all quartics with zeros, -3, -1, 1, and 2. All right, so if we're trying to identify which graph actually matches up with a function, we're going to need to figure out what does that a value look like. So let's look at an example of that. So a given cubic function has zeros at -2, 1, and 2. We know that the general equation for such a function can be written as f of x equals a x plus 2, x minus 1, x minus 2. If we let a equal 1, so if we say that a equals 1, then the equation becomes f of x equals, and we list our zeros, but we could put the a value in the front if we wanted to. Remember that a 1 is implied, so we don't have to write it, but if we wanted to represent that a in this case, we could say f of x is equal to 1 times x plus 2, x minus 1, x minus 2. Let's suppose that we have a cubic that passes through the point 3 to determine the a value. So we have the same cubic equation here. We're going to substitute in these x and y values. So we're going to sub x equals 3 and y equals 20 into our general equation for this cubic function. So we have f of x equals a x plus 2, x minus 1, x minus 2. Now we're going to substitute 3 in for x, and we're going to substitute 20 in for y, or f of x, right? Y and f of x are the same thing. So we'll substitute a 20 in on this side of our equation. We're going to leave a as a because that's what we're trying to find. And we'll substitute a 3 in for all of our x values. So now we'll just simplify where we can. So 3 plus 2 is 5. 3 minus 1 is 2. And 3 minus 1 is 2. And 3 minus 2 is 1. So let's multiply these values. 5 times 2 is 10, and 10 times 1 is 10. So you have 10a. We're going to divide both sides by 10 to isolate our a. And we will have that a is equal to 2. So we can say, therefore, f of x equals, and in place of our a now, we're going to put a 2. And then we will list all of our factors. And then that is the equation that represents a cubic function that has those zeros, but also passes through that point 320. All right, let's look at another example and write down the steps of how to find the equation. So for each of the following, find the equation of the polynomial function in factored form. So step 1, we're going to write the general equation. So we're going to write the general equation. So in this case, we have f of x is equal to some a value, we don't know what it is, and then we're going to put all of our zeros in brackets. So 0 of negative 3 is going to be x plus 3 as a factor. A negative 2 is going to be x plus 2 as a factor. And a positive 2 is going to be x minus 2 as a factor. So once we've written the general equation, we're going to sub in the given point. So we've been given a point, negative 4, 20, negative 4, positive 24 rather. We're going to sub that in for x and for our f of x. Okay, so in for f of x, we're putting a 24. We still don't know our a value, but anywhere we see an x, we're going to substitute in a negative 4. And then we're going to solve for a. So we'll say we'll simplify and solve for a. So let's simplify our brackets. So we have negative 4 plus 3 is a negative 1, negative 4 plus 2 is a negative 2, and a negative 4 minus 2 is a negative 6. So if we multiply those all together, we should get a negative 12a. And we'll just go over here to finish. If we divide both sides by negative 12, we should get a negative 2 equals a. And then let's just write our last step. We're going to write the equation with our a value. So we can say, therefore, now we have f of x is equal to, and we can write it with our a value. So we have negative 2, and then all those factors, x plus 3, x plus 2, x minus 2. Okay, so we have our general steps of what we're going to follow to figure out our a value and then write the equation as a result. Let's try one more together. So we have a quartic with zeros at negative 3, negative 1, positive 1, and positive 3. So let's start by just writing the general equation. So f of x is equal to our a value, and then all of our factors. Right in. So x plus 3, x plus 1, x minus 1, x minus 3. We're going to substitute in our given point, which is at negative 30 for our y, and 2 for all of our x values. and then we will simplify and solve for a. So 2 plus 3 is 5, 2 plus 1 is 3, 2 minus 1 is 1, and 2 minus 3 is a negative 1. So if we multiply all of those, we should get a negative 15a. And we'll come up here to solve again. So we're going to divide both sides by a negative 15 in order to isolate a. And we're going to find that 2 equals a. So we can say, therefore, f of x equals 2 times, and then all of our factors, x plus 3, x plus 1, x minus 1, x minus 3. Okay? Go ahead and pause the video and try C and D on your own, and then once you're ready, hit play again and you'll see the solutions for C and D. Okay, so there's your solutions for C and D. Take some time to look through and see if you have any questions. Then go ahead and try E and F. But before you try E and F, I just wanted to point out one thing. In E and F, you're going to see that you have some zeros that repeat multiple times. Right? You have a negative one that shows up twice. So remember, when we want to represent that we have a 0 2 times, we could say f of x equals, put our a there, and then x plus 1. And we would just say that we have that factor twice, representing that with an exponent of 2. And then representing that positive one, we'd have x minus 1. All right, so go ahead and work your way through E and F, and then check back in for the solution. The solutions for E and F have been written in now for you, so check your work, make sure you're comfortable with that. I'm gonna say pause the video one more time, and I'm gonna pull up Desmos just to answer number 4 for one of the questions we've worked through. So it says, use a graphing calculator or other technology to verify that the equations you generated in question 3 have the required zeros and pass through the given points. So I'm gonna substitute into Desmo this equation we got for 3a. So I'm gonna plug this one in. That'd be better, yeah. I'm gonna plug in f of x equals negative 2 times x plus 3 times x plus 2 times x minus 2. And we're gonna make sure that we have those zeros that were given to us and that the graph also goes through that point negative 4, 24. So let me pull up Desmos. Okay, so I've pulled up Desmos. Let's check to make sure our zeros are on this function. So we have a 0 here at positive 2. We have one at negative 2 and one at negative 3. So that's great. Those zeros check out for this function that we found. Now, if we also want to make sure that that point is on the function, we can go to our table of values in Desmo and look for a negative 4 in my x column. So we can see that at negative 4, our y value is 24. So the zeros that we identified in our functions, as well as the point that the function should pass through, look like those are all in our graph. And you can look at any of the other examples today and make sure that the zeros and the points are on the function when you graph them. That's it for your note for today.